Good afternoon, everybody, and welcome to the Presidential Faculty Award Lecture. I'm Christina Paxson, President of Brown. Now, some of you may know that these lectures are normally convened most often in the John Carter Brown Library, and under ordinary circumstances, we would have an audience packed into that just really beautiful and historic space. We have a good audience today, but much more dispersed. And like nearly all of our traditions, we've had to make adjustments so that this lecture is being delivered virtually. But that in no way takes away from the importance of the presentation we're about to hear. Let me give you just a bit of background. I established the Presidential Faculty Award Lecture in 2013. And the idea was to recognize members of Brown's distinguished faculty who are conducting especially notable and innovative research and scholarship. And recipients of this award are invited to give the Presidential Faculty Award Lecture to give faculty members, graduate students, and others from around the university an opportunity to learn about the work of leading researchers at Brown from their own, but also from other disciplines. So it's my distinct pleasure to recognize the recipient of the Spring 2021 Award, Professor of Engineering and Director of Brown's Institute for Molecular and Nanoscale Innovation, Nitin Padture. And his lecture is titled The Promise of Innovations in Solar Photovoltaics. And this will draw on his research in developing next generation solar technologies, which are leading the way in renewable energy, partly because the cost of solar has been steadily decreasing. So Nitin's research, as you'll learn, looks at the possibilities of bringing this technology out of the lab and into the marketplace. And that's the kind of innovation we need as our world faces the mounting crisis of climate change. I don't need to tell anyone here that sustainability is very much an issue that is at the forefront of public consciousness today, all of our thoughts. And in the coming decade, climate change and other environmental challenges will have profound impacts on the natural world and on economies across the globe. So Brown, as an institution committed to research and teaching, I think it's especially incumbent upon us to address these challenges. And Nitin's work is one fantastic example of the way in which Brown is contributing to this critical challenge that we collectively face. So I'm very much looking forward to hearing more about Nitin's important work. And I'd now like to invite Larry Larson, Dean of the School of Engineering, to introduce Nitin Padture. Thank you.
Thank you, President Paxson. It's really my honor and privilege to introduce Professor Padture today. Professor Nitin Padture is the Otis E. Randall Professor of Engineering here at Brown. He joined Brown in 2012 after distinguished careers at Ohio State University and the University of Connecticut. As President Paxson mentioned earlier, Nitin has been the director of the IMNI Institute here at Brown since 2014. And he's currently director of the Advanced Ceramics and Nanomaterials Lab in the School of Engineering. The talk that we're going to hear today is a really fascinating example of how Brown has taken a leadership role, a worldwide leadership role in a very, very important technology that has a major, major role in mitigating climate change in the years ahead. It's incredibly exciting research. We're going to have a really great time this afternoon. And Nitin, I'll turn it over to you. Thank you again.
Good afternoon, good evening, good night, good morning, wherever you are in the world. Thank you so much, Dean Larson, for the kind introduction. And thank you to President Paxson for this incredible honor. I'm really humbled by this honor. And thank you to all of you who are attending, and we would be meeting in person, but the flip side is that many people around the world are able to attend this event. So thank you for coming. So I'm going to talk about solar photovoltaics, but I included my middle name here for two reasons. One is that when I come from in India, your father's first name becomes your middle name. And so Prabhakar is actually my father's first name. So this is a tribute to my dad, who's an inspiration, who's a retired civil engineer in India. And the second reason I'm using this is because Prabhakar actually means light maker in Sanskrit, which is an epithet for sun. So when I talk about solar photovoltaics, I can say that my middle name is the sun. Anyway, jokes aside, this is the outline of my lecture. So I'll talk about the global crisis, climate change, which President Paxson already referred to. then talk about role of renewable energy in solving this crisis, and talk about silicon solar cells, which is the which is the established technology, and talk about a new emerging photovoltaic technology called Perovskite solar cells, and also present some exciting new research in perovskite solar cells, some of which has been accepted for publication in Science magazine recently. So I'm quite excited about sharing those results with you, and finish off with challenges and opportunities for innovations in solar photovoltaics. So global crisis, of course, climate change is a huge crisis. This is everybody's mind. And unfortunately, we cannot really vaccinate out of this crisis. And you may have seen this chart. This basically shows, okay, let me get my laser pointer. This shows CO2 emissions gigaton per year as a function of year. And these are the different models for basically what happens when you have CO2 emission in the atmosphere. So if we have status quo, then this is the worst case scenario. You have RCP. RCP is basically the greenhouse effect. We predict that global warming will be about 5 degrees Celsius, which is really unacceptable. And in order for us to meet the Paris Accord goals of 2 degrees Celsius and aim for 1.5 degrees Celsius, the RCP needs to come down, which basically means that the CO2 has to be reduced. Near zero CO2 emission is necessary to avert this irreversible climate change. And renewable energy has a very important role to play. And this chart basically shows the Earth power capacity. And on the left-hand side is all the finite sources and the relative values in this terawatt year per year. And these are all the renewable sources and all the different values. But you can see the point I'm trying to make is solar is sort of accessible in limitless source of energy. And I think everybody knows that. So just a primer for people who are not familiar with the units of energy and power. So energy is actually power times time, which is joule, and power is energy divided by time, which is watt. So these are some of the common units that are used. I just used terawatt year, and then another unit is called quad. And these are all the prefixes we use: 1,000, kilo, mega, giga, and tera. So to put this in perspective, the annual energy consumption of an average home in the US is about 10,000 kilowatt hour. And the annual energy consumption in 2019 of US was 29 trillion kilowatt hour, or 2.4 terawatts a year, or 100 quads. So this is sort of perspective. So let's talk about the established technology, silicon photovoltaics. So they're made from monosilicon, which is single crystal silicon, or multi-silicon, which is polycrystalline, has grain boundaries and grains. And they're fashioned into cells, which is about 5 watts per cell. And the power conversion efficiency of multi-silicon is about 16%, whereas monosilicon is about 21%. This is record efficiency in lab scale cells, and this is a theoretical maximum based on physics, is about 33%. So you string the cells together into a module, and the module is stringed together into a panel. So residential is less than 10 kilowatt, and then commercial is 10 kilowatt to about 1 megawatt. And utility scale is greater than 1 megawatt. So you see these solar panels as far as I can see. And these are the utility scale solar farms. So what's happening in the world is that there is an exponential rise in the capacity, installed capacity of solar photovoltaics. So you can see this exponential curve. And so we are right now at about 750 to 800 gigawatts. And there is prediction that by 2022 will exceed 1 terawatt, which is 1,000 gigawatts, which is really exciting. Now that was power capacity, installed capacity. This is actually energy, so actual energy. So this is generation on the left-hand side in the Sankey chart, and this is consumption on the right-hand side. So in 2019, there was 100 quads was spent in United States, and electricity actually contributes 37% of the total energy equation, and the demand is of course growing. And solar actually contributes about 3% of that electricity generation. Wind is about 7%. So we're talking about 10% solar photovoltaics and wind together. But there is potential for electricity to contribute to transportation when electrical vehicles, more and more electrical vehicles come online and reduce the dependence on petroleum. So demand, as I said, is going to be growing for electricity. So how much does this photovoltaic power plant cost today? So this is utility scale. So these are the solar farms. As you can see, they are actually much cheaper to build than residential solar photovoltaics per watt. This is the cost per watt. And these are all the different costs that are added. So I'm going to focus here on this PV module. So for example, in utility scale, that is a significant fraction of the cost of the solar photovoltaics. And by the way, these are certified for 20 years operation, and there is no fuel, of course. So this is all upfront cost for the rest of the life of the power plant. So let's focus on photovoltaic modules. And the price of photovoltaic module has been plummeting, and it's close to 30 cents or 25 cents now. But it is plateauing because of some fixed costs. And this is because the production rate is really growing exponentially, and 70% of the production actually is accounted by China. And this is what is leading to this rapid decline in the module cost. So today, a 6 kilowatt rooftop installation is to about $17,000, and about 10 years ago, it was $48,000. So you can see the tremendous attractiveness of solar photovoltaics. Now, this is what is called levelized cost of energy. So this is actually what you pay at the meter. And this includes all the costs, and of course, there's regional variations and so on. But this is coal is basically constant for the last 10 years or so. Nuclear actually is going up. Then we have gas. This is natural gas is going down. And this is onshore has reached about $41 per megawatt hour. And this is what is happening to solar photovoltaics. So this cost came down in 10 years. This is a tremendous amount. It's $40 per megawatt hour. And so this has basically achieved what we call grid parity, right? And this is before subsidies. And this is the 2030 goal, is to halve this cost of solar photovoltaics energy. So let's come back to the global crisis, which is climate change. And this is a sobering report that came out of International Renewable Energy Agency in 2021. And basically what it says is that even with the current policies, with so many renewables and so on, there's still going to be 31% increase in total energy use. And this is non-renewable and this is renewable. But if you want to reach the Paris goal of 1.5, actually you need to decrease the energy consumption by 22%. And the mix needs to be 74 renewable, 26 non-renewable. And they did a lot of analysis and came to the conclusion that by 2050, if you're going to achieve the Paris Accord goal, then the global solar deployment needs to increase from currently 0.8 terawatt to 14 terawatt, and wind from 0.8 to 8 terawatt, on a 10-fold increase. So this is really daunting, and I already see that so much excitement going on in solar, but getting to 14 terawatts is going to be a huge, huge challenge. So there are needs for innovation in order for us to do this, to go to 14 terawatt solar power, right? And so there are technological innovations, and this is sort of the classic definition of innovations per Schumpeter, which basically means that new inventions are coming to market, and we need innovation there for even more cheaper and more versatile solar photovoltaics than what we have now. We also need systemic innovations in terms of power grid and storage. And we'll also need financial innovations, because all these 14 terawatt solar panels are going to cost a lot of money, and you need to raise capital in order for us to do this. So all three need to happen in order for us to achieve this 14 terawatt solar PVs in the world, right? So I'm going to focus on the technological innovation first. And this is what's happening with regards to solar photovoltaics price. So this is the price per watt. And in the 1970s, it was almost $70 per watt. And this is the DOE, or Department of Energy, roadmap. And they've been really on target. Actually, the target has been beaten. So for example, in 2020, the average solar photovoltaic cost is about 30 to 25 cents per watt. And that has been amazing. But this is where we want to be. This is the next generation photovoltaics. It's going to be pennies per watt. In order for us to do this, we have to have certain requirements. First, has to be a cheap kind of material. It has to be earth abundant material, cannot be an exotic material. Has to be small amount of material, really thin films, or not wafers. And you should be able to make it at room temperature by solution processing near room temperature in order to save energy and make it cheap to make. And you cannot really compromise on efficiency, because solar photovoltaics, theoretically, they're actually not that efficient. And therefore, if you compromise on efficiency, you'll just need more real estate, and real estate really is at a premium when you have solar photovoltaics farms, right? So this is where we are in terms of efficiency. So this is the record solar photovoltaic efficiency progression. So these are lab scale records, and silicon photovoltaics, not much is going on for many decades. And silicon photovoltaics are about 20 micron thick wafers. So put this in perspective, the diameter of your hair is about 100 microns. So it's twice the diameter of your hair is the thickness of the wafer. It's quite thin. But then this is what's called gallium arsenide. This is sort of the Ferrari of photovoltaics. It's really well performing, but it is also extremely expensive. So typically used in satellites and things like that, and space applications. But this is thin film. So this is 5 microns. This is cadmium telluride. So there's a US company named First Solar, which commercialized this product. And about 10% of the solar photovoltaic installations in the US are made by First Solar, and they're not silicon. They're these cadmium telluride thin films, and they have relatively high efficiency. These are not yet commercialized, SIGs. And then there's the emerging photovoltaic technologies which have not caught up with the efficiency yet. This is dye sensitized, this is organic. But this is where the excitement is in the new photovoltaics called perovskites. So they were invented in 2009. So the efficiency has gone from 4% to today, which is certified at 25.5%, which is really rivaling silicon in the last 12 years. It's really amazing. And the beauty is that this is actually a 0.5 micron thickness film. You can see the difference between a wafer and a film like this. So the amount of material used is extremely small, right? And satisfies all the, so it has the potential to satisfy all the next generation photovoltaic requirements that I mentioned, including high efficiency. And that is why the excitement in this material. Also, if you have a new photovoltaic technology, it's not just going to replace the old technology. It has some new functionalities. So for example, it is a very tunable material, and therefore you can actually put it on top of silicon solar cell, and it absorbs the complementary part of the sun spectrum that silicon does not absorb, and you can actually boost the efficiency of silicon solar cell. So here's a case wherein you are collaborating rather than competing with an existing massive technology. So this is probably the lowest hanging fruit, which is going to come to fruition in terms of commercialization. Also, since they're so thin, they can be bent like this. They're very flexible. They can be used for portable power sources like drones, and you can also use continuous roll-to-roll printing for large area, very fast fabrication. And since you can tune their band gap, you can actually make them colorful and semi-transparent, so they can be integrated into buildings. And you can't really do this with silicon. And recently it's been discovered that they actually have unique properties in space. They're damage tolerant, radiation tolerant, and also self-healing. So this is a very exciting area, and I'll come to that later on in my lecture. So what's a perovskite? So perovskite actually is a family of complex crystal structures. It's named after a Russian count named Perovsky. And this is the general formula, AMX3. Of course, there's a huge number of perovskite compounds, but I'm going to be focusing on this organic and inorganic halide perovskite. So this is A in the cage, this is M in the smaller cage, and this is X. So the halide perovskites, A actually is not an element, it is actually a molecule. So it can be formamidinium, or it could be methylammonium. M can be lead or tin, and X can be halogen, which is iodine, bromine, or chlorine. So a prototypical compound would be MAPBI3, or we call it MAPI very fondly, right? So you can just remember MAPI. Now, of course, you can mix and match. You can mix and match and make alloys, and so there's thousands and thousands of compounds or possibilities here, right? Compare this with silicon. So silicon is quite boring. It's only one atom, one kind of atom in a fixed crystal structure, so it's not very tunable and can't do much. This is very obvious to us that this can be very tunable at will, and of course, it's sort of a playground for physicists and chemists and material scientists. All right, so what happens with light absorption? So this is a semiconductor with a PN junction, has a band gap, and when light enters with energy greater than the band gap, then what happens is that you get a promotion of an electron from this valence band into this conduction band and creates a hole. So missing electron is basically a hole. And because of the way this PN junction is structured, the electrons are whisked away this way and the holes are whisked away this way. That generates electricity, right? So light absorption is very important for photovoltaic material, right? So this is the solar spectrum, and this is light absorption of silicon. This is absorption coefficient, which is a log scale. So this is silicon. So silicon actually is not a very good absorber, light absorber, but we use it because it's cheap and it's established technology. This is your Ferrari of photovoltaics, gallium arsenide. And look at MAPI. This is the perovskite, which is actually made in sort of quick and dirty way, has even higher light absorption compared to gallium arsenide. So this is enough for people like us to dance in the streets, that this tremendous light absorption. So this is key to making good solar cells, is the good light absorption. So as I said, it's unprecedented light absorption in perovskites, and there are several other properties, sharp absorption transition, defect tolerance, and so on, which has sort of come together like a perfect storm in these perovskite materials. So how does this perovskite solar cell work? So here's your perovskite semiconductor. It has multiple layers. This is glass, this is a transparent electrode. So you have to have what is called an N-type electron transport layer and a P-type hole transport layer and a metal electrode. And this is an electron micrograph of a cross-section of a solar cell made in our lab. So light enters, creates an electron hole pair. The holes go this way, electrons go this way, deeper into the material, electron hole pairs are generated, holes go on top, electrons go on the bottom. So by the time light has actually passed through this half micron, it is completely absorbed, mostly absorbed, and it's done its job, which is really tremendous compared to, say, silicon, which takes 200 microns for this to work, right? And of course, what happens is that holes cannot go this way because of this filter here, N-type filter, and electrons cannot go here because of this P-type filter. And of course, there are many different kinds of architectures and mechanisms that are still being understood and so on. But this is the gist of how perovskite solar cells work. Now let's talk about processing. So compare this with silicon. So silicon, you have to use ultra high purity material, has to be melted at very high temperature, above 1425 degrees C, which is where silicon melts. For multi-silicon, you can cast it. For single crystal silicon, you have to grow this into a boule very carefully. This is actually a similar silicon that is used in your computer chips. So single crystal without any grain boundaries. And the wafers are sliced from this, and it takes about 5 tons of silicon to make a megawatt worth of silicon photovoltaics. Perovskites, on the other hand, can be processed very easily because they're hybrid inorganic crystalline. Their melting point is quite low. And the beauty is they actually dissolve in organic solvents at room temperature to form solutions. And once you have these solutions, we can do what is called solution deposition, crystallization of these films using what we call benches and beakers approach. And you can make continuous films, uniform films over large areas at relatively low cost. And here's a picture of a top view of a thin film made in our lab. And this is a cross-section of a thin film made in our lab. So as you can see, it's quite thin, about 500 nanometers or so. So people have been working on scalable manufacturing of this, of course, because we have to make this into large areas. And there are several methods used. And use these, and then you make solar cells out of it, large area solar cells, right? And you can also use this roll-to-roll printing to make solar cells very cheaply and fast. And so what's happening in the field is people have been focusing on efficiency. The efficiency is really very high, very competitive. Then of course you have to scale everything up. Otherwise it's not very useful. You have to have meters and meters square of solar cells. But the next hurdle is stability, because what makes these materials easy to process also makes them easy to degrade. And therefore stability is very important. So you have to beat this dichotomy of this easy to make and easy to degrade dichotomy using some innovations in chemistry, physics, and material science. And then next one is reliability, because these solar cells have to last for 20 years outside in the element. And so this is where the bottleneck is now with stability and reliability. And this is where my research group is working in. And I'll give you a couple of examples, one on stability and two on reliability relatively quickly, just highlighting the results. Okay, so here's the perovskite thin films. So they're polycrystalline, as I mentioned. So they have these grains. So these grains are single crystal. And then these are grain boundaries where the grains actually meet. So that's where the grain boundaries are. And this is actually a micrograph from Rothman, which basically shows the atoms and the grain boundaries and so on. This is a high resolution transmission electron micrograph. So the grain boundaries actually influence solar cell performance and stability quite dramatically. And therefore, what we need is grain size, which is much larger than the thickness of the film. And that is basically a requirement. So it reduces the density of these grain boundaries and increases performance and stability. I'll give you one example. So here's a in situ transmission electron microscopy of a MAPI film. And this is done at Brookhaven National Lab, which has very special transmission electron micrographs. And this is the work of my postdoc, Hadash Turnlicht. And basically you let in air into the transmission electron microscope. And what happens is you'll start to see degradation, but the degradation sort of decorates the grain boundaries. So it's preferentially attacking the grain boundaries. So if you increase the grain boundary or the grain size or decrease the grain boundary density, then you'll make this material more stable. But there's a problem. The problem is that the grains don't like to grow in thin films. So when they reach the size of the thin film thickness, they stop. And so here we're going to use FAPI, and FAPI is formamidinium instead of methylammonium. And what is unique about FAPI is that it actually has two polymers. MAPI only has one polymorph at room temperature. One is the alpha perovskite, which is what we need for solar cells, and this delta non-perovskite, which is not very useful, right? And as nature has it, whatever is useless actually is always easier to make, right? So delta non-perovskite is easier to make, but it's not very useful. But my student, Srinivas Yadavalli, PhD student, basically figured out a way to take advantage of that. So he can use this transformation from delta to alpha and basically grow these very large grains. So here is how it goes in a nutshell. So this is a very fine grain thin film, about 0.2 microns grain size, and the thickness is 0.5 microns. So this is not very acceptable. And this is this delta phase. And then he heat treats this in what's called a solvent vapor. And what happens is because of the solvent vapor, it nucleates these alpha perovskite grains, and they grow at the expense of this matrix and grow into large grains and giving grain size 5 microns in a 0.5 micron thin film. So it's really tremendous. So if you look at the cross section, you can see the thickness of the film and you can see the distance between the grain boundaries. It's really amazing. And here's some videos that basically show what happens when you change the temperature for the nucleation. So this is what we need, where you need a low nucleation density, because when they meet, they'll form large grains. If you have high nucleation density, then when they meet, they will give you fine grains. So this is what Srinivas used to get something like this, right? So now let's look at the performance. So this is fine grain, and this is X-ray diffraction pattern, which basically shows that this is before. Of course, it's black because solar cell materials are black. They absorb light. But when you treat this is sort of a severe treatment, 70% relative humidity or room temperature, 40 hours. This film is transformed to delta. It's become transparent. You can read what's behind the thin film. And the efficiency of these solar cells is about 16% or 70%. Medium is somewhere in the middle, but when you have these coarse grain materials, the efficiency has jumped to 19%. And after this, you still see that the film is actually black. So now what we have done here in coarse grain thin films is not only improved efficiency, but also stability in these perovskite solar cells. So of course, these perovskites are made at a relatively low temperature and using chemistry, and therefore we can actually functionalize these grain boundaries. So the grain boundaries may not just be where the grains meet. You can actually make them smart. You can put functional moieties here like polymers, or you can put molecules. And as I said, because of the room temperature processing, you cannot really do this in, say, ceramics and metals, because the processing temperatures are so high, the polymers or molecules will simply burn. Here, we have this advantage. And a couple of examples, this shows where we put this polymer in the grain boundaries, and this polymer is hydrophobic, so it repels water and increases the stability. And here is a case where we actually put molecules in order to pacify the grain boundaries in this particular solar cell. So let me talk about reliability now. So we talked about stability. Let me talk about reliability. And as I said, these are multiple layers, and these multiple layers in a solar cell have different materials, and they have different thermal and mechanical properties. And when you go through thermal excursions during processing or during service, they create residual stresses or thermal stresses, which can be detrimental to the performance of a solar cell, right? And if you have flexible solar cells, in addition to this, when they undergo severe bending and twisting and stretching, and they actually have more severe stresses than the rigid solar cells. And again, the mechanical properties of perovskite is actually quite poor. Again, same dichotomy. That it's easier to make, low temperature melting, then they have poor mechanical properties. The elastic modulus is 17 GPa. You may not know what this number means, but this is actually 1/10 of what silicon is. And the hardness is also about 1/10 of silicon. So they're very soft and they're very compliant, and they're also very brittle. They have low toughness. And interfacial toughness, for example, the interface is even lower. And therefore, we need to actually toughen these interfaces to prevent delamination, because if delamination occurs here, then the solar cell is basically dead, right? And so we took it upon ourselves to toughen the weakest interface possible, and that's between the perovskite and the ETL or the tin oxide interface. And again, in solar cell motto is do no harm. You can toughen interfaces many different ways, but you might kill the performance of the solar cell. So you can't do that. At least maintain the performance or make it better. Only then these structural approaches are going to work. And this is the work of my PhD student, John Dye. And this is what he has done. So this is a perovskite thin film, and this is the ETL. And basically, we have used a molecular glue here. Again, I don't have cannot tell you all the details here, but this molecular glue improves the adhesion of this weak interface. Right? And he measures the toughness by applying load. And what he finds is that there's about 50% increase in this toughness going from a control without the glue to with the glue, and sort of approaching the single crystal value or the toughness value of the perovskite itself. So it's really an amazing achievement. And this work is going to appear in Science in 2 or 3 weeks. So let's look at photovoltaic performance. So here we have made these solar cells. This is controlled solar cell without the glue, and this is the one with the glue. We can't really tell the difference because the glue layer is a molecular layer at this interface here, right? And then let's look at the solar photovoltaic performance. This is what's called current density, and this is voltage. So many of you may not be familiar with this, and this is under 1 simulated sunlight. So this is called open circuit voltage. So at 0 current, this is open circuit voltage. This is called short circuit current at 0 voltage. And this is called maximum power point. So this is where the solar cell will produce the maximum power, and this is where it would operate to produce electricity, right? And this is called fill factor. So you want these curves to be as square as possible. So you want to make it less square, then the fill factor becomes less than 1. So you also want to maximize the fill factor approaching 1 in order to get the maximum out of this solar cell, right? And then the efficiency is basically this Pmax divided by the 1 sun that we put on multiplied by 100. So these are some numbers. So the control, you can see it's about 20% efficient, whereas with the glue, we not only improved the toughness, but we also improved the efficiency. And this is primarily, okay, so this is some statistics. We do a lot of solar cells to do this. This is actually a photograph of the solar cell. And this enhanced efficiency is primarily due to increase in this VOC because of reduced electron hole recombination that the glue affords at that interface. So this is a functional glue, right? So now let's look at operational stability. So this is normalized efficiency. Again, I'm just presenting here one data set. We have many other data sets, and also I don't have time to present all the underlying science that went into actually making this happen. So this is normalized efficiency. As you can see, the control efficiency is dropping. This is continuous 1 sun. These are naked solar cells, not encapsulated at room temperature. And the efficiency is degrading, whereas one with the glue is going strong. So for example, we can calculate the life of the control is about 700 hours under this continuous illumination. And when we break open these solar cells after testing, what you find is there's voids and cracks at this interface. And that is because this interface is not very tough. But when you toughen the interface with this glue, the projected life here is actually about 4,000 hours. And when you break open the solar cell, you see that the interface is relatively pristine. It doesn't have this nearly damage-free interface, doesn't have these holes and cracks, right? So now we have enhanced efficiency, stability, and reliability using these interesting approaches. Right, so the second reliability thing I'm going to talk about, topic I'm going to talk about is flexible solar cells, and very briefly. So flexible solar cells approach we are taking here is not only toughening the interface, but toughening the perovskite thin film layer itself. Because as we know, this perovskite layer is actually quite brittle. So we can toughen it, but again, same motto goes, do no harm. Either maintain the photovoltaic efficiency or improve it. Otherwise, it's not going to fly. And this is the work of my PhD student, Min Chen. And this is a testing device that he has. And it basically shows fatigue testing of these solar cells, right? And this is the data. So this is actually efficiency, absolute efficiency. You can see the efficiency has been improved from control to this toughened perovskite thin film, and it lasts more than 10,000 hours without degrading as much as the control film. So this basically shows you that it's enhanced efficiency and reliability in these approaches. All right, so what is the outlook for perovskite photovoltaics? As we saw, it has the potential to satisfy all these requirements, and progress is being made all over the world, from efficiency to scalability, reliability, and now stability, and now reliability. And as I say, this is such fascinating materials. It's impossible to let go. We have to improve upon all the other shortcomings in order to take advantage of this tremendous light absorption capacity this material has. And research is really the key to reaching its full potential. And I must admit, as a scientist and engineer, it's scientifically so exciting. It's just fascinating materials and just amazing materials to work in. Of course, there are numerous challenges, and there are companies, startup companies and big companies working on solving some of these challenges. But as I said, the research is really key to bringing it to commercial fruition. It's not commercial product yet. All right, so I would be remiss if I didn't mention that a lot of this builds on a NSF project that we just completed. And this is all the technical achievements, many technical achievements. Involved 8 faculty members from 3 different universities. We're also proud of other activities we did, like outreach to K-12 students about solar energy, then undergraduate research internship, partnering with Tougaloo College in Mississippi, to HBCU, then graduate research and entrepreneurship training, junior faculty mentoring, and many public outreach events such as online PV course, SciTunes, scientific cartoons, and public lectures. And also happy to report is that this Brown Space Engineering, which is a student-led organization, launched a CubeSat, which was really successful, and now they're about to launch this PBDX in 2024. And the perovskite solar cells are going to fly on this satellite because of this unique advantages perovskite solar cells have in terms of radiation resistance and self-healing, which other solar cells do not have. And the students just learned that their proposal was approved by NASA, so this is going to happen in 2024. So really excited about that. Finally, what are the challenges? Coming back to the challenges, we need 14 terawatt solar power, solar photovoltaics by 2050. And technological challenges are that there is really inconsistent government support for R&D, and things like subsidies sort of incentivize status quo rather than technological innovation. So some of those things need to be changed, or at least corrected. Then systemic challenges, there is really sluggish development of renewable compatible power grid. And financial challenges are this: you're going to need tremendous opportunities, investment opportunities to build 14 terawatt solar power, right? So there's a lack of capital and investment opportunities. And also solar power, which is kilowatt hour, is sort of a low margin commodity, right? So I'm not an economist, but my son Siddharth is an economist, and he works at a CO2 startup in Berlin, and he reads The Economist and sends me these solar articles. And this particular sentence caught my attention from that article he sent me, that solar PV industry boasts no giants comparable to those in aircraft manufacturer, pharmaceutical, let alone computing. No solar company has a market capitalization over $10 billion, and no solar CEO is in danger of being recognized on the street. So this is actually maybe why there is a dearth of entrepreneurs in this space, and that is something to be concerned about. In any case, there are opportunities for innovations to get to this 14 terawatt solar power by 2050. Technological innovations, as I said, if we increase funding for this next generation photovoltaics, they will be invented and commercialized. They could be even cheaper and more versatile. So perovskite is just one example that I gave you. Then this needs to be systemic innovations, so modernizing of the electric grid. So right now there's only 10% solar, wind, variable renewables being used in the United States. So grid can handle that. When it goes to 70%, the current grid cannot handle that. So there needs to be complete overhaul of the electric grid in order for this to work. Otherwise it's not going to work. And also you need storage, because the sun only shines in daytime. So you need to have utility scale storage that is affordable, that's low loss, that is rapid response, and so on. And of course, if you want to build these 14 terawatt solar panels, you will need to attract capital, equity capital and debt capital from both retail investors and institutional investors. So institutional investor, I'm talking about retirement funds and insurance companies and banks and bonds and things like that. So there are some innovations such as tax-free MLPs, or these are sort of bundled investment opportunities that are publicly traded on Wall Street. And it also needs federal loans, which they don't contribute as much, but they can use to leverage other investments, right? So as I said, all three innovations need to happen. And some closing thoughts is that renewable energy revolution is inevitable. In some ways, it's actually necessary, right? And solar PVs, as I mentioned to you, are at the frontier of this revolution. There's sort of a sense of urgency in this happening. And so future significant fraction of electricity actually is going to be harvested from the sun. So we better get used to it. So this is actually a fascinating book, which is a great resource. And I would encourage you to read this if you want to learn more about innovations in sort of photovoltaics by this young gentleman, Varun Shivram. Now, again, US government is putting money where its mouth is. So recently this was announced that the goal is to cut the solar cost by half. And there's large investments being made in research. And I'm happy to report that Brown University, my group, was a beneficiary of one of the major grants. And this is in collaboration with NREL. And also thank you to Brown University for providing the cost share. And the US Energy Secretary Jennifer Granholm, when during the webinar where she made this announcement, said all these words: 100% renewable energy by 2035 in US, net zero carbon emissions by 2050, and one of the fastest and easiest paths is through solar. So we need to grow the capacity by hundreds and hundreds of gigawatts in America to accelerate the fight against climate change. And we need to act as if our hair is on fire. So there's really a sense of urgency that she conveyed at this fascinating webinar. Anyway, so I'd like to acknowledge in closing, and my tremendous group, Min Chen is PhD student, Zheng Hong Dai, Srinivas Yadavalli, Hadash Turnlik, Kostak, Hector. I'm just listing who contributed to the work that I presented. And this is contributing former members who are gainfully employed. These are the Brown faculty members I've collaborated with over the years. In particular, Yu Chi has contributed to this recent work that is going to be published in Science. And then new collaborations with National Renewable Energy Lab, Joe Berry and Kai Zhu, collaborate with Dalian University of Technology on this flexible solar cells, and also with Michael Gretzel from EPFL in Switzerland on this flexible solar cells. The funding was provided by National Science Foundation and Office of Naval Research, and grateful to Brown for all their support, Provost Office, Office of Vice President for Research, and School of Engineering. And thank you for your attention. And this is my research group. And I hasten to add that this is actually a pre-pandemic photo, so no mask here. We had no clue that there was going to be masks coming. But thank you very much. And if your questions don't get through, then please feel free to send me an email and I'll be happy to answer your questions.